Hi, this is ET370 Lecture 9. This is going to be a three-part series, so this is actually the first part. In this first part, we're going to talk about CMOS transistors, which is actually a complementary metal oxide semiconductor, or that's what it stands for. And we'll look at two implementations. One is an inverter, a logic gate, and a NAND logic gate. And in the second and third part, we're going to cover just the formal look at logic operators in general. So we'll look at the inverter and NAND for the second part of this lecture 9. And the last part, we'll look at OR, NOR, and exclusive OR. Okay, so let's dive into CMOS. And basically, all they are is just a combination of NMOS and PMOS that we looked at in lecture 8 and 7. And they are going to be very useful for creating logic operators. And like I said, we're going to look at the inverter and NAND, but these are kind of all of them, right? And NAND or exclusive OR inverter like I have here. And what's an inverter? Well, it's very simple. If you have an input to this gate, if it's high, it's going to make it low. If it's low, make it high. And this is what the symbol looks like. It's a little triangle here with a circle, and you have an input and output. But let's look at the physical implementation. Okay, now just to clarify for us, a logic inverter does not mean DC to AC, although we can use it in a, what do you call it, DC to AC inverter, but it's purely just, off or low to high, high to low, okay? And so this is an implementation. So let's just look at the left here. If we look here, it's just a combination of, like I said, PMOS and NMOS, right? And so you can see here, I have a voltage input. Look how the gates of both of these are tied together, right? Remember, the input gate voltage drives the PMOS and NMOS, and you have the drains tied together here, and the source and source here. And look how the PMOS has the PNP structure, and the NMOS has the NPN structure. Okay, so you get your ground and your voltage, right? So you do have to supply this with some kind of logic voltage, right? And here's the symbol for this, right? So you get your PMOS and NMOS. Look at the arrows. The arrow goes in, the arrow goes out, right? Opposite of a BJT. But the output voltage here is actually measured at the drain. Okay, it's hard to see here, and that's why it's more clear there. Notice the drains are connected. And so here's the symbols, PMOS, NMOS. But the whole thing combined here would be a CMOS, and it directly implements an inverter, right? Okay, so you're basically combining, combinations of NMOS and PMOS give you this CMOS. So this is your inverter implementation. And by the way, it does look like a half bridge that we talked about in the last part of lecture 8, right? So you get the PMOS on top, the NMOS on the bottom, right? Okay, so how does this work? Now, if you recall the way a logic drives an NMOS and PMOS, a high voltage shorts, maybe basically these are like switches, shorts the NMOS, but turns off or opens up the PMOS. And a low voltage, what does that do? Opens the NMOS and closes the PMOS, all right? So we can look at this side, right? So if I have an input voltage that's high, well, what's gonna happen? If I have this high and I short this, I'm essentially shorting the output to ground, which means that I get 0 volts. So high voltage of the input creates a low voltage on the output. And don't forget that PMOS actually opens up. The inverse is true when I have the logic input or the VN low. What's going to happen? It's going to turn on the PMOS. So this is going to be shorted essentially, and this is going to be open, right? And so now you can see this voltage is on the output is brought up to the high. Okay, not too bad. Let's go to the next one. So the next one here is an AND or a NAND, actually, right? And so before we talk about the NAND, let's just talk about an AND. And an AND, if you have two inputs, this is the symbol, by the way, it's this kind of bullet-shaped symbol, two inputs A and B, and these are all the combinations. A can be 0 or 1, B can also be 0, 1, but you have 0, 0, 0, 1, 1, 0, 1, 1. These are just all the possible combinations. What we call this, by the way, is a truth table, right? And we look at what are the outputs. For an AND, right, both of these must be true. So that's only the last row right here. Okay, so false, false, false. Good. So A and B looks like this. If I want to make it an inverter or a NAND, I can put a bar over the top. Look, I have A, we'll talk about this later, but A multiplied by B is an AND, right? And A multiplied by B with a little bar on top basically just inverts the output. And look at this, I put a little circle here. Okay, and we'll talk about this again in the next lecture, right? And so you can see how to create an AND or a NAND. So what we're saying is, let's combine NMOS and PMOS, and we call that just CMOS, in a way that we can create this truth table. So we'll have two inputs and we'll have this as our output. Okay. All right, good. Let's keep moving. And so what does that look like? It looks like this. And I know it seems a lot more complicated, but notice there's 1, 2, 3, 4 MOSFETs, right? All combined together, we call this CMOS, and this is creating a NAND gate. Notice there's 2 input voltages and 1 output voltage. And like I said, I know it looks a little crazy, but look at this. The A here is attaching to this PMOS gate and that NMOS gate, and the B here is attaching to this NMOS gate and this PMOS gate. Notice these two PMOSs are in parallel. They're all connected to these two NMOSs, which are in series, okay? And the voltage out is the connection here. So you have 2 series, 2 parallel. These are PMOSs, these are NMOSs, okay? And what we want to see is that the output voltage is going to match this behavior, a NAND behavior, right? Okay, so let's just walk through the different rows here and see what happens. So what happens if we have a low voltage and a low voltage? Well, if we have a low voltage here, what happens? This PMOS turns on and this one opens up. Same with this one. If I have a low voltage here, this one also turns on, this one opens up. So 0, 0 actually make these shorted and these open. This voltage is going to be pulled up to VDD. We're going to get a high. You can see that here. Short, short, open, open, voltage becomes a high. Okay, what happens if I do this? 0, 1. Okay, if I do 0, 1, 0 is not going to change. I'm still going to have a short here and an open. If I have a 1 on here, this is going to be open and this is going to be shorted, but it kind of doesn't matter because this one dominates and you still are going to get that same behavior of a high voltage. This is going to be pulled up to high, right? Okay. What about this 1, 0? Well, it's kind of the same thing. If this is now 0, look at this. This is going to short and this is going to be open. It doesn't really matter what these two do, and you're still going to get a high voltage, right? And that's over here. And then the last one, well, if I pull both of them high, then what's going to happen? If this is high, this is going to open. If this is high, this is going to open. So these are now both open and these are now both shorted, which means I'm going to pull this down and I'm going to make this a 0 voltage output. Okay. All right, so I hope you can see that this combination, this configuration of NMOS, PMOS is going to create a NAND behavior. And the beauty of being able to physically implement this is now we have a way of actually making these logic gates. And what we'll see in a later lecture is that a NAND gate can actually create every single logic gate. So that's really nice, okay? So once you make this, combinations of this will make any logic gate you want, and then we get the really cool computers and transistors and all the computation and video cards that we see today. Okay, all right, I'll see you in the next lecture.